Okay, so today we're looking at the fundamental theorem of calculus again. We're going to look at some examples and then so little different examples from what we saw in the previous lesson. We're going to start off just basically, doing some review of what we saw. So that's what we're going to look at here first. But when you look at the fundamental theorem of calculus and you're evaluating with limits, when you're evaluating any integral with limits, what you want to keep in mind is the result is always a number. Okay, so if I've got limits, A and B, whether it's -3 to 2 or whatever, that result should be a number when I get done. Okay, so if we look at example number 1, starting off with what we talked about again in the previous lesson, the first thing we need is an antiderivative for this integral right here. So the antiderivative of 6 is 6x. The antiderivative of -x is going to be -x. We're going to add 1 to the exponent, that's squared. We're going to divide by 2 again. And then the integral for, or the antiderivative for x squared is x cubed. And we need to divide by 3 because there's no 3 in front of that x squared. All right, and then we want to evaluate this from -3 to 2. So we're going to plug in 2 first. We're going to do 6 times 2 minus 2 squared over 2 minus 2 cubed over 2. And then we're going to subtract, and we're going to throw some parentheses in there again. We don't want to forget those. And we're going to plug in -3 for x. 6 times -3 minus -3 squared over 2. And finally minus -3 cubed over 3. All right. Okay, so at this point, if we were doing this on an AP test, we could quit right there. And since I don't have the answer in front of me on this one, I'm going to quit right there. I don't feel like doing all the math on this one. All right, take a look at the next one. We need the integral from 0 to pi halves of sine x. Well, what function gives a derivative of sine? That's going to be cosine of x. But if you think about the derivative of cosine, cosine has a negative derivative, and this sine x is not negative, so we're going to put a negative in front in order to cancel out the negative from the derivative. We're evaluating from 0 to pi halves. So we're going to plug in pi halves first. That's negative cosine of pi halves minus a negative cosine of 0. All right, so we've got, cosine of pi halves is 0, so that's 0. The two negatives make a positive, and cosine of 0 is 1. Okay, so take a look at number 2 versus number 3. The only difference between number 2 and 3 is in number 3, it's the integral, again, from 0 to pi halves of 5 times sine x. Well, one of the ways you can look at this is any multiples like that 5, they can be pulled outside the integral. And normally I probably wouldn't do this, but you can anytime you want to. And the reason I say I probably wouldn't do that is because once you recognize that this is just the integral of sine x from 0 to pi halves, all you have to do is multiply that result by 5 when you're all done with it. Okay, so if it's easier, you can pull the 5 outside. If it's not, you can leave the 5 in the integral. But I've already done this integral in example number 2, so I know that this integral is equal to 1, and I would just multiply that by 5, and I'm going to end up with positive 5. All right. Next one, we have the integral of secant x tangent x. So we want the antiderivative of secant x tangent x, which is secant x. Secant of x, and that is positive. Again, we're going from 0 to pi fourths here. So secant of pi fourths minus secant of 0. Okay, so secant of pi fourths, that's the reciprocal of cosine of pi fourths. Cosine of pi fourths is root 2 over 2. So if you flip that over, you get 2 over root 2, which is equivalent to root 2. And then secant of 0, that's the reciprocal of cosine of 0. Cosine of 0 is 1. And so secant of 0, the reciprocal, is also 1. And we're going to leave that one like that. All right, I would encourage you to turn off the video, try these last two on your own before we get to the back side here. Okay, so the first thing I'm going to do is I'm going to rearrange this equation just a little bit here. I've got 3 minus 6, and I'm going to bring the x squared up into the numerator again, raise that to the negative second power. Now I'll integrate. The integral of 3 is 3x minus 6 times x, and if we add 1 to the exponent, that becomes negative 1. And then we want to either multiply or divide by negative 1. I say either one here because multiplying by negative 1 is the same as dividing by negative 1. So that's going to leave us 1 to 2 with our limits again. So if we plug in 2, we would have 3 times 2. And then the two negatives are going to turn to positives. So that's going to be plus 6. And then the x to the negative first, I'm going to drop that back down to the bottom. That's going to be over 2. Minus, and then we'll go to our parentheses again here, 3 times 1. And then again, it's going to be plus and 6 over 1 here. Okay, so if we add all that stuff up, we're going to actually end up here with 0. I'll let you take a look at that. All right, and finally number 6 here. Again, we need an antiderivative here. So the antiderivative of x squared is x cubed. Remember, adding 1 to the exponent, dividing by the exponent, minus 4. And since there's not an x on the 4, we just include an x. And we're evaluating from negative 2 to 2. All right, so starting with 2, this would be 2 cubed over 3 minus 4 times 2. Minus, and then again, don't forget your parentheses, negative 2 cubed, negative 2 cubed over 3, minus 4 times negative 2. And let's see here. I'll leave the addition to you guys, but this turns out to be 16/3 over here. And then minus 16 inside here, I believe. Does that sound right? Actually, let's see, you get minus 8 and minus 8. So you know what, I've already combined those. You know what, I'm just going to take this off. I'll give you the answer here. It's 32/3 here. 32/3. All right. And I would encourage you to mess around with those fractions again, just to make sure you get that same value. All right, number 7. We want the integral from negative 4 to 4 of x squared minus 4. So you'll notice it says the absolute value of x squared minus 4. Absolute value of a function means basically that entire function needs to be above the x-axis or greater than or equal to 0. So in other words, this part that's down on the bottom here, this part of my parabola that's down at the bottom here, to take the absolute value of that, what we want to do is we want to bring that up to and above the x-axis here. And so we're going to do that. We're going to flip this parabola that's below. We're going to flip it up and back down like that. So really, if we're going to go from negative 4 to 4, we're looking at negative 4 over here. So we need this area right here between the curve and the x-axis. We also need the area to the right side between the curve and the x-axis. And now instead of the area below, we want this area up above. Okay, so when we go to do this, we have to look, we can't just take the integral from negative 4 to 4 of x squared minus 4, because otherwise we'd have some negative area down here, and that area above the x-axis is all positive now here. So we're going to end up writing 3 integrals for this. We're going to write one for this first part over here on the left side. So we're going to write one for the left, one for the middle, and one for the right side here. So I'm going to do the integral from negative 4 to negative 2 of x squared minus 4. That's the left side, times dx, plus the integral from negative 2 to 2. Now here's the thing, it's not x squared minus 4x, it's now negative x squared plus 4. Negative x squared plus 4. times dx, because when you flip the parabola over, like we did when you reflect it over the x-axis, you're basically negating both parts of the equation there. And then we need the right side of the parabola as well, so we're going to do positive 2 to 4 of, again, the original function x squared minus 4 dx. Now, we can save ourselves a little bit of time here, because if you look at this, the area over here on the left is the same as the area over here on the right. So what I'm going to do is this. I'm going to take these guys, which are the same. Okay, so these guys are the same. And so what I'm going to do is I'm going to rewrite this as 2 times the integral, and I'm going to do the positive side from 2 to 4 of x squared minus 4 dx, plus the middle section, which is still negative 2 to 2 of negative x squared plus 4. So instead of doing this 3 times, I only have to do it 2 times. All right, so my first integral, the 2 is going to stay there, and the 2 is attached to both parts of this, so we could do a couple of different things here, but I'm just going to attach it to both antiderivatives here when we go to plug in. So the antiderivative of x squared is, let's see, let's do it like this. X cubed over 3 minus 4x. And we're going to evaluate that one from 2 to 4. And then the second one is going to be negative x cubed over 3. And that's going to be plus 4x. This one we're evaluating from negative 2 to 2. All right, so the first one here, we've got 2 times, and we're going to go ahead and plug in 4. That's 4 cubed over 3 minus 4 times 4. And then I need to subtract 2 times, let's see, 2 cubed over 3 minus 4 times 2. Okay, so I'm just putting the 2 on there. I could have also put the whole thing in parentheses and put the 2 on the outside. It doesn't matter. The 2 gets attached to all of it, so it really doesn't matter how you do it. Second one here, we've got negative 2 cubed over 3 plus 4 times 2. And then we're going to subtract. This time I am going to use the parentheses because this is negative 2 cubed over 3 plus 4 times negative 2. All right, and again, I really don't feel like adding that all up. If you really want to, you can, but I'm going to leave it. All right, number 8, you'll notice it says absolute value again of sine of x. So I'm going to start by graphing sine of x. Sine of x goes from 0 to 2 pi. It starts at 0, it ends here at 2 pi. It has a middle point right here at pi, and it goes up to 1. Okay, so the first part of the sine graph would look like this, and then the second part actually comes down to negative 1, down here like this, and back up. So that would be sine of x. But we want the absolute value of that, so again, this part that's down below the x-axis here, we're going to bring that up above the x-axis here, and we're going to look at the area here on the left and here on the right. Now, because sine is basically the area in the sine curve on the left is the same as the sine curve on the right, one of the things I can do here is I can set up the integral a couple of different ways, and I'm going to show you both of those ways here. So I could do, if I was looking at it one way, I could do the integral from 0 to pi of positive sine x dx plus the integral from pi to 2 pi, And because I reflected it over the x-axis, this would now be negative sine x dx. Or, since those two areas are exactly the same, I could simply do 2 times the integral from 0 to pi of sine x. And I will get the same answer either way. I think it's easier to do the second one. So the integral of sine x is cosine of x. But remember, cosine has a negative derivative, so I need a negative in front, and I still need the 2 in the front. And we're going to go from 0 to pi. So if we plug in here, we get negative 2 cosine of pi minus negative 2 cosine of 0. And this turns out to be cosine of pi is negative 1 times negative 2 is 2. And then we're going to subtract cosine of 0, which is 1. And 1 times positive 2 is 2. So we would have 2 plus 2, which is going to equal 4. Okay. So if I did that correctly, we should end up with 4 there. All right. Number 9, given f of x equals 9x plus cosine of x, and capital F is the antiderivative of lowercase f, with f of 4 equal to negative 4, find f of 3 using the fundamental theorem of calculus. So if this is an initial value problem again, so we have we have a derivative function. We're supposed to evaluate f of 3, and the only thing we know about the original function is that f of 0 equals negative 4. Those are both x values. So if I'm going to use the fundamental theorem of calculus, these x values, I'll call this x1 and x2, these x values become the limits on my integral. So what I want to do is I want to find the integral from 0 to 3 of 9x plus cosine of x dx. And I know that that will equal capital f of 3 minus f of 0. Okay? So when I think about the fundamental theorem of calculus, typically we go ahead and we plug these limits in as we find the antiderivative. We would plug in 0 and 3, which we're going to do, but we don't normally do this on the right side. But with an initial value problem, we can set up the fundamental theorem of calculus as f of b minus f of a. And so that's exactly what I'm doing here. I'm still going to find the antiderivative on the left. That's going to be 9x squared over 2 plus sine of x. We're going to evaluate that from 0 to 3. And on the right-hand side, we don't know what f of 3 is. We're going to find that in just a minute here. And we're going to subtract f of 0, which is negative 4. All right, left side, let's go ahead and plug in. This is 9 times 3 squared over 2 plus sine of 3 minus, let's do our parentheses again, 9 times 0 squared over 2 plus sine of 0. And hopefully you're already thinking, hey, everything in those parentheses is 0 right there, which it is. Okay. On the right side, we have f of 3 plus 4, because of the double negatives there. So on the left side, we've got basically 81 halves plus sine of 3. 81 halves plus sine of 3. And that's going to equal f of 3 plus 4. If we go and subtract 4 on each side, all right, I need to do 81 halves minus 4, which leaves me f of 3 equals, and remember, 4 is 8 over 2, so we're really doing 81 halves minus 8 halves. That's going to be 73 halves plus sine of 3. So that's how we would do that problem using the fundamental theorem of calculus. Now we're going to do it again, and we're going to do it using initial values. Okay, so when we say initial values, what I'm going to do this time, and by the way, I'm not really sure where that came from, so we're just going to cross that out. When we say you do this using initial values, what I want to do this time is I want to look at f of x, okay, the derivative portion. So I know that f of x is equal to 9x plus cosine x. I need an antiderivative for this, so I know that capital F of x is again going to equal 9x squared over 2, so it's the same antiderivative, plus sine x, plus some value of c here, okay? And now I can plug in 0. F of 0 is equal to negative 4. So when I plug in 0, I should get negative 4. Now, again, I'm going to go through and do the steps here, but hopefully what you can see is that c has to equal negative 4 here. All right, if that's not making sense here, then let's keep going here. So I'm gonna plug in negative 4 over here on the left. Negative 4 equals 9 times 0 squared over 2, little squished here, I know, plus sine of 0 plus c. Well, you can see that 9 times 0 squared over 2 is 0, sine of 0 is 0, and so we end up with c equals negative 4. Okay, so now my function reads f of x, capital F of x, the original function, is 9x squared over 2 plus sine of x, and then minus 4, and now I can plug in 3 again. So now I would have to find f of 3 by plugging in 3, and so if we do that again, we're going to get 9 times 3 squared over 2 plus sine of 3 minus 4. Again, 9 times 3 squared is still 81 halves. So 81 halves minus the 4 is going to give me exactly what we got above. F of 3 equals 73 halves plus sine of 3, and we get the same value for f of 3 there. Okay? All right. Let's see what we have in this last page here. Okay, you know what? I'm missing a page. Give me a second here. Okay, I found my last page here. Didn't have it in that set of notes there. So, all right. So this is applying the fundamental theorem of calculus using a graph of f prime to find absolute extrema. Okay, so typically we would find absolute extrema if we had a function. We would be looking at critical points. We would be looking at endpoints. And so what they've given us this time is a little different situation here. It says let lowercase f be a function defined on the closed interval -6 to 6 with f of 0 equal to 3. The graph of f prime, the derivative of f, consists of 4 line segments and 1 semicircle as shown in the figure to the right. Find the absolute maximum value of f of x over the closed interval -6 to 6. Okay, so again, thinking about just what do we know about absolute maxes and mins. Okay, so first thing we want to do is identify critical points. All right, so we're going to start off with that. Identify critical points. All right, critical points. So critical points are, again, where the derivative is equal to 0 or the derivative is undefined. Okay, so I'm looking at the graph of f prime of x, and this derivative is not undefined anywhere. Okay, this particular derivative is not undefined. This derivative does have some zeros at -4, -2, +2, and 5. So my critical points would include x equals -4, -2, 2, and 5. Now, one of the things I can do is I can check all of those points, or I can try and figure out, hey, are some of those, do I know if those are maxes, if they're mins? So remember, we're looking for the absolute maximum. So let's look at some of these values here. So if I look at -4, for instance, all right, my derivative is negative, and then it changes to positive at -4. So if the derivative is negative, f is decreasing, then f goes to increasing, which means that -4 is actually a minimum. Okay, so I really don't even need to check this. This is a minimum on f of x, so I'm not going to worry about that guy. And then if you look over here at +2, the same thing is happening. The derivative goes from negative to positive at +2. So +2 is also a min. Both of those guys are mins here. Okay, so I don't even have to worry about those. So we're going to skip those all together. So I've got two critical points, -2 and 5. The other thing I need is endpoints. Endpoints. Okay. And my endpoints are -6 and 6. So, and I don't have a function here. I don't have anything to actually plug these into, but they did tell me that f of 0 is equal to 3. Now, again, think of this as an initial value problem. Okay, so the first thing I want to do is I want to use x equals -6. Okay, so what I'm going to do is this. Here, I'll put a little note over here, x equals -6. So if you think about this, if I look at the integral from -6 to 0 of f of x, or in this case, I'm going to say f prime of x, because that's the graph that we have, times dx, that is equal to f of 0 minus f of -6. Fundamental theorem of calculus. Okay? So the difference is I can't find an antiderivative for f prime of x, but I can find the area under the curve from -6 to 0, because these are all straight line segments in a half circle on this graph. So the next thing I'm going to do is I'm going to go through here and I'm just going to start to section off my graph and find each of the areas under these, or between the graph and the x-axis. So this first one, this is just a triangle. So we have base times height, 2 times 2 is 4 divided by 2. This is below, so this is going to be -2. The second area, base times height, that's 2 times 1 is 2 divided by 2, that's +1. The next one is half of a circle. The area of a circle is pi times the radius squared. The radius here is 2. 2 squared is 4. This would be 4 pi for the whole circle. This is half a circle, so this is -2 pi because it's below. The next triangle, base of 3, height of 2, that's 6 divided by 2 is 3. And my last little teeny tiny triangle over here, base and height are 1, and divided by 2 is a half, and it is below, so the area on this last part is -1/2. Now, what that's going to do for me is it's going to allow me to come over here and say, okay, well, let's look at the integral. Let's look at the area from -6 to 0. So let's add all that up. We have -2 plus 1 is -1. And then we're only going to 0, so really you could look at it like this. This is -pi over here. This is -pi over here. Okay, so we have -2 plus 1, which is -1, minus pi gets me all the way up to 0. So we're at -1 minus pi. That's the integral. Okay, that's the left side of this. And that is supposed to equal f of 0, which they told us was 3 at the very beginning, minus f of -6, which is what I'm trying to find here. Okay, now the way I'm going to solve this is How do I want to do this? Let's see here. I'm just trying to think of the easiest way to do this without running out of space here. Let's go ahead and subtract 3 on both sides. So I'm going to do -3 here, -3 here. And that is going to give me -4 minus pi equals f of -6. Oops, excuse me. Negative f of -6. And then I would need to divide out the negative, so that would give me +4 plus pi equal to f of -6. So there's the value of f of -6. That's the left endpoint. All right. Okay, let's do the next one then. We need to do x equals -2. So let me write the integral here first. So we're going to come down here, x equals -2. So this time it's going to be the integral from -2 to 0 of f prime of x dx. And this time that'll equal f of 0 minus f of -2. All right, so here we go again. I need the area under the curve from -2 to 0. So I'm going to start with that, -2 to 0. That's just negative pi. All right, look at that. That one was easy. Negative pi. That's going to equal f of 0, which again is 3, minus f of -2, which is what we're trying to find here. So this time I'm going to do something a little bit different. I'm going to add pi to both sides, and I'm going to add f of -2 to both sides. Think about that. I'm going to add pi, so I'm going to bring the pi over with the 3. That's going to be 3 plus pi. And then I'm going to add f of -2 to both sides, which is going to bring the f of -2 over to the left. And that's going to equal 3 plus pi. Okay, so that's the value of f of -2. Next one we need is f of 5. I would encourage you at this point to try these on your own and see how you do. The difference in this case is that the integral now goes from 0 to 5 of f prime of x dx. Oops, f prime of x dx, there we go. And that's going to equal f of 5 minus f of 0. All right, so let's take a look at this guy. I need the area from 0 to 5 this time. 0 to 5. All right, from 0, we're looking at negative pi plus 3 gets me all the way up to 5 here. Negative pi plus 3. So the left side is negative pi plus 3. The right side is f of 5 minus f of 0, but you remember f of 0 was 3. So all I have to do is add 3 to both sides. So I'll do that this time. I'll go ahead and add 3. And so that's still negative pi plus 6 now equals f of 5. All right, last one is x equals, oh, I already did -6. Okay, I just need to do +6. So we're going to do x equals 6. So now we need the integral from 0 to 6 of f prime of x dx. That's going to equal f of 6 minus f of 0 again. Still using f of 0. That's our initial value here. All right, so let's go look at that entire integral all the way up to 6. All right, so we know that it was negative pi plus 3, and 3 minus a half is 2.5. So we're going to say that this is negative pi plus 2.5, which is 5 halves. I'll do that, 5 halves. And that's going to equal f of 6 this time, minus f of 0. And f of 0 again is 3. Okay, one more addition here, and I think we got it. All right, So I'm going to go ahead and add 3 again. 3 plus 2.5 is 5.5. So this is negative pi. And you could just say plus 5.5 if that's easier. It's not a big deal. And that's equal to f of 6. All right. We need the absolute max. All right. So negative pi, that's, again, pi is roughly negative 3 plus 5.5. That's about 2.5. Negative pi plus 6 is going to be about 3. And then we've got 3 plus pi, which is even bigger. That's about 6. And then we've got 4 plus pi, which is a little bigger than 3 plus pi. So it looks like our absolute max is right here. All right. The absolute max, of f of x on the interval from negative 6 to 6 is 4 plus x at x equals negative 6. And we're done.